Thank you very much for being here today. My name is Mohamed Elsakhawy, and today we'll be speaking about a deep dive into Linux networking. There's lots of diagrams in the presentation, so bear with me in that. Some of them need some sort of pointing, so I'll be pointing a lot at the screen in here. Just bear with me for that. So the agenda we have today first will be, why are we having this presentation? Why is it important actually to know the Linux network stack? And then we'll be explaining a little bit about network stack, its layers, what's sold within Linux. We'll talk about some core concepts. There's lots of pieces in it, so some pieces are very important to know in order to understand the transmit and the receive paths. We'll be speaking about the role of the NIC driver, what does it do within the context of the network stack, and some important structs that are used to do network manipulations in the network stack or within the driver itself. We'll be quickly looking at the network transmit and receive paths, basically based on all the things that we mentioned up here. We'll be applying that and how they are used basically to allow the traffic to flow in and out of Linux system. Then we'll be looking at the challenge of small packets. This is a very important challenge in a virtualized environment. So we'll be looking specifically at what challenges face packets when they flow through a network stack, when they're small, and in a virtualized environment, and some solutions that we can use to tweak that. So why this presentation? The importance of this presentation basically because of this diagram. This is basically an expression about the complication of a network stack of Linux for receive path. This is a project by Adrian Maheu. He tried plotting the network receive path, and it's available on GitHub. And this is the only one that's available right now. The transmit path, I think it was in progress, but it wasn't done. But this is the path that a NIC takes for receiving a packet. For sending, that's very similar to that. But basically, as you see, there is lots of pieces in it to get the packet from the NIC to the application that's running in the user space. And this, yeah, just part of it. I actually had to crop some piece at the end because it just wouldn't fit. So as a Linux engineer, you don't need to know everything in the Linux network stack. You could get along with your day with just regular knowledge about Linux networking, how to send a packet, how to receive a packet, and so on. However, knowing is extremely important when you work in the admin/operations field, because there's lots of pieces that you can tweak carefully, and they will allow you to either troubleshoot issues, or they will allow you to improve the performance of the application running in the user space. So the network stack, the Linux network stack, it looks like that, and it's very similar to the OSI model. We'll look at the bottom at the physical layer where you have the actual NIC itself. On top of that, you have the link layer where you have the MAC addresses, the manipulations by the driver at that point. You have the IP layer, which basically is doing the IP or UDP protocol, IP protocol. And then on top of that, you have the TCP or UDP protocol. On top of that is socket layer, which basically acts as the interface for your user space application. And then you have the application layer on the top. Net filter, which many of us use IP tables for the filtering or firewall D, it basically acts as hooks attached to these. So your filtering happens in parallel to those paths. So as I mentioned, it's responsible mainly for the network transmit and receive. It provides an abstraction layer such that you as an application developer, you don't have to care about the NIC that sends the packet at the end of the day. All you care about is to be able to deal with the socket layer, and then everything will get translated at the end and you will reach the NIC and be sent successfully. It's reachable by syscalls from the user space, and it can be divided into those components as I mentioned, and packets flow down for the send and up for the receive path. Net filter, as I mentioned, is engaged using hooks to basically do manipulations on the traffic. So the core concepts we need to look at first before we describe the transmit and receive path, and some of them are actually very hard to explain without a full picture of the network stack itself, but I'll try my best to basically try explaining it without going far into the receive and the transmit paths. So the first thing is a user space versus kernel space. What are the differences? We'll look at what's named as NIC, TX, and RX rings, which descriptor rings and the packet buffers. We'll look at an IRQ, interrupt request. We'll describe what's DMA, the NAPI versus interrupt-driven receive, RPS, RSS, and RFS. And all of these acronyms I'll explain in detail alone. And finally, we'll be looking at the QDisc, which is queuing disciplines within Linux, and this is very important in the transmit path specifically. So the user space versus kernel space in Linux is basically a logical segregation of privilege. It allows applications to run in a more contained way in user space where they can't mess heavily with the hardware or the operations of the operating system. So applications for users run in the user space. They don't do any kind of hardware manipulations. They have very limited access to memory except the kind of memory attached to that particular application. And they can't do manipulations for the CPU, for the memory management unit, MMU, and so on. So there's limited access when you're running in the user space. NIC drivers and any kind of kernel operations run in the kernel space. It was more privileged mode. You have access to the entire memory. You have direct access to hardware, so you can set registers, which is extremely important basically to deal with any kind of hardware attached to your system. You need to be able to think around basically with the registers on the host to be able to tell it where to copy or receive packets from. Memory management, CPU, also happens in the kernel space, and access to memory regions, and this is extremely important when it comes to how hardware copies data into the memory. So this only can happen within the kernel space. There is some implications to having that, which I'll explain at the end of the presentation, and there are some solutions to improve that and move it to user space. So the access to memory regions in the kernel space is sort of controlled, so hardware needs to be right to specific areas that it has access to, and that's where the DMA comes in, which again I'll explain in the next slides. The most important thing is to understand that there is a logical segregation of privilege that exists between users running in the user space and the kernel space, and that the kind of permission that are available for an application is very limited when it comes to user space versus the kernel space, which can actually access the hardware itself. So the second concept we want to talk about is IRQs and soft IRQs. So interrupt requests are basically things or signals that are raised by hardware when they need the operating system to do something. So when you have, in the context of network stack, when you have a NIC, it receives a packet, it needs to be able to tell the operating system, I received this packet, go and process it. And this basically is using an interrupt request. In order for the operating system to basically execute something, it needs to know an associated interrupt service routine, or ISR. It needs to know exactly what should I do when I get this kind of request. ISR is essentially they explain to the Linux kernel what to do with this particular hardware, piece of hardware basically exists. And when it raises the signal, what should be done in it. There is a problem, however, with IRQs. They're basically the blocking. Whenever a CPU receives it, it has to service it, and it has to acknowledge that this has happened. And obviously, if we have lots of packets being received in a NIC, we need to be able to process them and not log the CPU for every single packet. And pushing a packet through the network stack has lots of layers, as we've seen in the first slide about network stack. So we want to minimize the amount of time taken by an RQ processing, which is ISR, in the kernel. So the CPU basically stops what's doing, serves this particular IRQ, and we can't do that for every particular packet that comes in. And this is where the soft IRQ comes in. Soft IRQs are basically interrupts generated by the kernel itself. They're named sometimes as the upper and lower half of the ISRs, which basically divide what's lightweight and can be done by locking the CPU, and what can be scheduled for processing later on. So soft IRQs basically do the heavy lifting. So whenever you want to process a packet, the NIC receives the packet, it raises the interrupt, and IRQ gets serviced. That's really fast. And then something is scheduled in the context of soft IRQ to basically process the packet, send it up the network stack, which takes much more time basically than IRQ servicing. So this is not blocking, it acts as a regular thread, or basically a thread running in the kernel space, so it doesn't require a CPU to stop what's doing. So NIC, RX, and TX strings. So for a NIC, basically when it receives a packet, it needs to be able, so this is actually, I can maybe point it much better here in this diagram. So on the bottom here, we see the NIC itself. It's attached to a kernel space memory structures. We have the TX and RX, which are memory regions in the kernel. Those are set up by the kernel, by the network driver. The packet buffers on the left are also memory regions to store the packet contents. And we'll ignore the ones on the right-hand side for a sec until we explain these ones. So basically, when the NIC receives a packet, it needs to know where to put it. And the RX rings will basically contain memory regions or memory addresses to where the NIC can actually write this packet. So RX and TX are ring implementations. They're usually named as descriptor rings, and they contain descriptors to where the NIC can put the data. So it doesn't actually contain the packet contents, and those are usually small in size. When they're filled up, they basically overwrite because it's ring structure, and that's where basically you can see packet drops. Because if you fill it really fast before you can copy, which rarely happens, usually the trouble happens with the processing above that. But basically, a NIC will pull an RX descriptor, copy the data into the packet buffer, and from there, the data is available in the memory. So again, the RX rings and TX rings, they don't contain the packet data. They contain addresses in memory for the NIC to write the packet contents to, or the frame at that level. So they're called, as I mentioned, descriptor rings. Packet contents are stored in the packet buffers, in here on the top left, and those memory regions are DMA-able. And by that, I mean it's direct memory access. So the CPU does not have to be involved in copying the data from the NIC to the packet buffers. Basically, the NIC will get an address, write the data directly to it, and we literally save the CPU any cycle to do any kind of copying data in this place. So as I mentioned, yeah, the NIC would receive something, will basically be the RX and TX strings. TX strings act as the opposite of the RX strings. They will basically contain addresses in memory for where the packet contents are. So if you want to send something, it will basically be copied to the packet buffers. A TX descriptor ring will be created here, and then will be pushed down to the NIC to send it out or basically flush it over the wire. So DMA, as I mentioned in the earlier slide, so DMA basically allows a NIC to write the data directly to the packet buffers without having to go through the host CPU. And this is extremely important because you don't want, for every single packet that the CPU also stops what's doing, copy the data from the limited memory that's over the NIC, and then put it in the memory. So this is fairly standard right now on many devices, not only for NICs. And there is some sort of security implications with that. This happened in the kernel space, so everything basically is very privileged at that point. However, when we discussed at the end of the presentation, there are ways to move this to user space, which becomes very risky at that point because you're literally accessing the user's memory regions. So the DMA engine basically on the NIC would be copying the data when it receives it to the packet buffers using the RX descriptors. As I mentioned, the RX string will contain pointers to RAM locations where to write the packets to. And as I mentioned also, we save the host CPU cycle basically for copying. So the flow will be basically as follows. You receive something on the wire. The NIC will do its modulation, demodulation over that, translate the electrical signals to digits, zeros and ones, and do from there get an RX string. An RX string would contain a descriptor, so we will know where to copy our data to. The NIC will then use DMA to copy its contents, the data contents basically to the packet buffers. And at that point, it can raise an interrupt to the operating system and say, I have a packet, go service it. Oh, sorry, something is. So before NAPI, so as I mentioned now, there is an interrupt. So once the NIC will copy the data into the memory, it raises an interrupt. This is a problem because we can't raise an interrupt for every single packet that we receive. It has very high overhead to basically do that. So here, when we get on the wire, and then it goes to the NIC, we raise an IRQ. So if we do this for every single packet that we get, the CPU will literally have to stop for every single packet, service it, which is very high overhead. And generally speaking, when we receive a packet, we know that this is a sequence of packets coming through. If someone is watching a YouTube video or if servicing an HTTP request, all of this, it's not going to be served in a single packet at the end of the day. It's going to be a series of packets that have to be dealt with. And that's where NAPI comes in, which is a new API. NAPI works more in a mix between interrupt-driven and the polling mode. And it works literally as follows. Basically, an interrupt is generated for the first packet, and interrupts are then disabled. Whenever the device is put, I'll go maybe through it again from start. So NAPI will basically go through interrupt-driven first. such that you can actually deal with the first packet that you receive. And then the device will be put into polling mode. So next packet that arrive, they don't do any kind of interrupts for the NIC. It keeps looking at the device in polling mode. If there is no packet, interrupts are enabled. So the sequence basically works as, if you get a packet, you know that you're getting more packets throughout the flow. So what you do is you disable interrupts, keep polling the device every certain interval for packets. You don't find the packet, then you start enabling interrupts again. If you find the packet, you pull it up, and this way you have saved many interrupts to happen for every single packet came in. So this is again a diagram for this. You receive a packet on the wire, it goes to the NIC, and from there an IRQ is raised. This is the first packet we're talking about. It goes to the CPU and starts servicing it. NAPI starts then polling that particular device and seeing does it have new packets or not. In a single queue NIC, so basically as we've seen earlier, NICs put their data that they receive in a particular TX and RX queue and from their packet buffers. So in a single queue NIC, by default, the CPU that services an interrupt, it's the one that processes a packet and push it up the network stack. So at some point when we pull that packet and start pushing it to the network stack, there is a problem that we have a single CPU doing that. Right now, NICs have more than one core, and NICs have more than one queue, and systems actually have more than one core. And better performance can be achieved by assigning more cores towards the queues that are available. And this is extremely important when you're dealing with high latency applications, basically, or they're implicated by very high latency, that you don't want the packets to sit idle in the queue for long. You want to be able to process them as soon as they arrive. And that you can do that basically by assigning more CPUs to that. But you cannot achieve better performance by assigning the CPUs randomly. You can't just assign those CPUs to the queues in a random order, and we'll explain that in a sec why this can't happen. But what will happen basically in the flow is you will receive a packet, it goes to the NIC, and then an IRQ will be raised. One CPU will handle that queue and start processing the packets for it. But as I mentioned, order of the packets is very important. So you cannot just assign packets that come in randomly to CPUs that are available, because the result of that is not going to be as performant as when you assign flows to it. You want the same flow of the packets, so if you're dealing with the HP request, to go through the same CPU core. This way, if this CPU core is overloaded, the packets will still arrive in order to the application consuming it at the end of the day. So we need to assign flows to CPUs. At a very high level, flows are same source, same destination IPs. There is more tuples into that, so there is more criteria that can specify what exactly is a flow. And we'll explain in a sec basically how NICs deal with that. But based on this, we can say that if this packet is coming from this source and going to this destination, then assign it to the same CPU as the previous packet that was doing the same source and destination. This way, the packets for this particular flow will always arrive in order. So as I mentioned, you receive something over the wire, then you have a NIC here, and then you raise an IRQ. If you assign it randomly, so a certain queue to any CPU, what happens when you assign to that particular red CPU one packet in that flow and it's overloaded? The packets will arrive out of order. You will have issue that basically the application cannot do anything until this particular packet on the red CPU gets processed. And so in a multi-queue, multi-core scenario, that's where functions such as RPS, RSS come in. RSS is basically receive-side scaling, and it's hardware implementation over the NIC, where it does match flows to CPUs. So it's, again, as I mentioned, multi-queue receive. NICs have multiple queues on them, and we have multiple cores. We want to do the mapping between them, and we do that based on the flows that we have understood over time. So basically, it creates a hash table. Based on the hash table, we know that this CPU will process this particular flow, so we keep that flow always going to this same CPU. However, not all NICs have RSS enabled on them as a feature, basically. Some NICs have only single queues. If you're looking at any commodity NICs, basically the ones that we have in our laptops, they don't have multiple queues. So that's where RPS can come in. RPS is basically an emulation for RSS at the software level. It does that by basically, instead of doing the computation over the NIC, it does that by assigning that task to a CPU. So the CPU basically becomes the dispatcher that computes the hash and based on that specify where the packet gets processed up the network stack. So again, it directs packets to a specific CPU for processing. One CPU receives the interrupts and computes the hash for this particular packet and knows the flow, and determines which CPU should process it based on the previous history that we know. If it's a new flow, then we basically assign it to one CPU, and we keep that in our hash table, so we know that for the next packet of that flow, we just assign to the same CPU. So as you see here, basically we're looking at receiving packet over the wire. It goes to the NIC, CPU that's basically responsible for determining, which is basically when RPS is enabled, this is the functionality of RPS. This CPU will determine who processes this packet and sends up the network stack. So we now assign flows of packets to CPUs, to particular cores in the CPU. However, RFS, or receive flow steering, it actually does a little further than that. And what does it do is it assigns the packets to a CPU where the consumer application is running. So if you know that Apache is running on core 0, and basically the packet that come in, you want them to go to core 0. This way you always get a cache hit, or at least higher cache hit than if you assign it to a different core. So RFS tracks a consumer app in the user space, know that this application received this packet, so it keeps track of that and keeps associating next packets with the same CPU. So obviously this works hand in hand with RPS, and the importance of this is that you avoid as much as possible cache misses for this particular core. Flow processors assume basically flows are processed on the same CPU core that where the app itself is running. You get higher cache hits and better performance at the end of the day. So again, so here you can see in the bottom, there is the wire, we go to the NIC, and from there, RFS, which is basically looking at the application layer. It knows which application consumed this packet, and based on that, on the next, it keeps learning, keeps knowing in the hash tables. And then next packets will basically be assigned to the CPU where the application itself is running. So the last concept that we want to talk about is queuing disciplines, and this is part of the Linux traffic control, which basically does allow you to play around with how the traffic for the network card goes out. It happens at layer 2, and it's very important when it comes to packet transmission, because you can think of them basically as policies for packet transmission. It has many policies that you can apply. One of them is very common, which is first in, first out. But basically, it allows you to play around with how the packets get sent out before they leave the host. So if you see here, basically the application will be lots of layers in between, reaching the queuing disciplines, and then a rearrangement basically in the driver queue. And that actually will be signaling to the host, not actually an IRQ. And then the NIC would do a DMA for that particular amount of basically packets to be sent, and will be sent on the actual NIC. So queuing disciplines play in the middle. You can specify policies in them, but they sit in the transmit path if you enable them. And lastly will be the NIC driver. So the NIC driver, it runs in the kernel space. It has 3 core functions for it. The first is to allocate RX and TX queues, which we explained a bit earlier. It has also to initialize the NIC, because the RX and TX queues are in the memory of the host, so the NIC has to know where are they in the network, in the memory of the host. So it initializes registers on the host to base in the NIC to know where those RX descriptor rings are. And also it would have to handle interrupts by registering the interrupt service routines. So for the NIC driver to operate, it has to use some structs which are defined by the kernel itself. The very important structs to know about is the net device struct, which is basically used to specify a device. And this is just a quick screenshot of it. And the skbuff, which is, this is the very popular one that I think everyone knows about. It basically is the structure used to represent a packet. And it goes with the packet throughout all the layers of the network stack. So whenever the packet is received, it basically, whenever the packet is received by the NIC, it will generate an skbuff with the pointers to where its data is located in the packet buffers. So it doesn't, skbuff itself does not contain the actual data, it contains pointers to where it's stored. And as I mentioned, it exists an implementation of all the OSI layers. It's unique, so each escape buffer basically is unique for every particular packet, and it has pointer to the next escape buffer basically exists in this reception. It's shared between multiple network stack layers, but some do manipulations in it, and some have to do cloning of it. So who creates the first escape buffer for a packet when it gets received? Obviously, it is the driver. And this, again, is just from the, I think, kernel.org. They had, the kernel.org, they basically had a small diagram explaining where it is, and the head and the end. So what you see here is basically head, the data, the tail is basically pointers to where it exists in the packet buffers. Okay, so this is, in a very high level, the network transmit and receive paths. So in the left-hand side here, we see the application, and the application user space. It's generating a packet. The first thing it deals with is a socket layer to basically be able to interface with the kernel space and start sending the data. Next to that will be the network stack. So we go down the layers. We go through the TCP UDP layer, the IP layer, and then the data link layer, and that's where the queue disk will come in place, and we'll start rearranging the packet based on the flow disciplines basically we specified. We have the driver queue at that point, and the TX string, so it's basically how we specify to the NIC, this is the data we want you to send. And then we have a signal that gets sent to the NIC, which tells it DMA those packets, put them in the wire, and send them out. When the data moves to the right-hand side on the bottom, we are faced first with the RX string, so the NIC goes RX string. Do I have enough memory space to actually put this packet? If yes, then it will DMA that to the packet buffers, and then will IRQ and NAPI will be involved to keep whether servicing it in the proper way, or the old way, which is IRQ, or NAPI way, which is basically a hybrid between interrupt and polling. We have the RPS at that next level, which basically does the packet steering. On top of that, we have the network stack, so the rest of the layers of the network stack. And then we have socket layer, and then this gets translated up to the application itself in the user space. So the NIC receive path will basically be looking as follow. We get a packet at the NIC here in the bottom. It goes to the TX, or the RX strings basically pull a descriptor. From there, it gets the descriptor, copy it to the packet buffers, and from there, it will raise an IRQ handler, basically, specify that I want to process interrupt, and the device will be put on a NAPI pull list, and then it will be pushed up the network stack using soft IRQs. The transmit path is a bit of the opposite. However, queuing disciplines, as I mentioned, are engaged in that. So application runs in user space. When a packet is ready to be sent, a send to call is received, is called, escape buffer is created, constants are put in the packet buffer, queue disk gets control of the queue, basically what gets sent out first, and so on, and the TX descriptor rings are set, and then next it picks up the TX descriptor and starts flushing it over the wire. Sending path also includes DMA, so the memory is copied from the memory of the host, or the packet is copied from the memory of the host directly to the NIC. It doesn't get stored on the NIC itself, or doesn't need a CPU to copy the data over. So as you see, the path has lots of pieces in it. It's not a simple path. This happens for every single packet that gets sent out. So obviously, if someone is downloading a big file, this happens for every single packet that goes through that. And we haven't even showed here any kind of net filter hooks that get engaged if someone is doing any kind of firewalling on the host. So a packet is the smallest unit in the IP layer. Generating too many packets will have improvement on latency, so you can send them faster. However, the throughput of that will be much low. NFV, or network function virtualization, love it. If we're doing also VoIP, VoIP loves smaller packets. Jumbo frames do the opposite, basically. It's a bigger frames, larger packets, higher throughput, but very higher latency as well. So we need to basically reach some sort of middle ground where the packet size does not impact the latency as much, but we still can fill a 10 gig pipe as well. So it's cost-benefit analysis for that. For small packets, we want the least involvement of network stack. Obviously, if a small packet, we want a very low latency for. If network stack has to do lots of processing to get the packet to reach the user space, this is all added latency. So the challenge becomes even worse when it comes to a virtualized environment because of this. We have here, this is a server basically. On the bottom we have the physical NIC of the server, we have the network space of the host, and on top we have a virtual environment, a VM, that has actually also on top of it a network stack for that particular VM and has userspace program. So a single packet flowing from the NIC on the bottom to reach that particular application on the left-hand side, the small one, or even the application on the right-hand side has to go through many, many hoops for that. So this is obviously a big problem, and most of the network now deployments happen in a virtualized environment. And most of the deployments now we use such as OpenStack, VMware, and so on. There is multiple layers for virtualization, and the network stack has to be engaged in every single packet that gets received or sent. So the network stack on the host and also network stack inside the VM have to be engaged for every single packet. It is very expensive overhead for every packet, and small packets basically mean even higher overhead. If you're sending too many small packets, then this path has to be engaged multiple and multiple times for a single task, basically. So saturating a 10 gig NIC, and this is an experiment I did a few years ago, we couldn't ever saturate a 65-byte MTU. We can't saturate a VM's 10 gig pipe. So it was always reaching 2 or 3 gigabits per sec within a VM in the user space. So basically, if you're running a server that's doing 10 gigs, which is pretty old nowadays, you cannot reach this 10 gig at a 65 byte MTU on the VM. So there are some solutions that allow you to bypass the network stack on the host. So network stack is important to have on the host, but however, if we're replicating it inside the VM itself, it has very little added value basically for that. The first one we'll talk about is VFIO and IOMMU, which basically work hand in hand to allow a device to be visible in the user space with some sort of security around that. And you'll be able to deal with it as if the VM will be dealing with the physical device directly using pass-through, but in a more secure way. Because again, DMA is a big problem when you let it run around and start copying data directly from memory. So you want to make sure that whatever happens in the user space is very controlled, because this is basically the difference that we have between kernel space. We know that whatever is running in the kernel space is privileged, but in the user space, it's not privileged, and it's shared between multiple users. So this solution basically allows us to move the NIC to the user space. So when you have a server, it's not visible anymore, this NIC, it's not visible to the server itself, it's visible to application user space as if it's device identified in user space. But however, something needs to manage this NIC in user space. Again, there is lots of functionality. There is the NIC driver that needs to allocate and deallocate the TX strings. There is the interrupt service routines and so on. So how do we do that? And also, we cannot have a physical NIC for every VM. So if we have tens of VMs on the host, we cannot basically allocate a NIC for everyone. So we need some way of sharing this NIC securely between multiple VMs in a virtualized environment. But in the same time, we need to do that with something to be able to manage it. So one of the solutions basically for that is DPDK-enabled OVS or Open vSwitch. And one other solution is SR-IOV, which I'll explain now. So moving the NIC to user space, basically we need to be able to do the same functions that the kernel or the network stack did for us. We need to be able to access the NIC's onboard registers, specify the memory regions to copy and process data from and to. We need to be able to handle interrupts. So we're basically saying we're ignoring the kernel, but still having to replicate some sort of its functionality in user space. We need to be able to allocate memory to DMA from and to. And VFIO and IOMMU, as I mentioned, they work hand in hand. VFIO is a driver, so it basically allows you, and this was told to me a few years ago, the VFIO allows you to poke a hole inside the network stack. IOMMU, it's literally the functionality within the hardware that ensure the security for that particular DMA. So it allows you to bypass the network stack of the host. So this is traditional, as we mentioned, the NIC will be there, we have TX and RX strings, we have the driver running there and the packet buffers. it will look like that in a VFIO IOMU enabled environment. You have just VFIO in the kernel space, so you literally poked some sort of hole in that kernel space, and you have those user space TX and RX strings and packet buffers. So VFIO, it's passed through style drivers. It's predated by UIO, which is an older one, less secure driver. It maps user space memory to regions at DMA. So this is important because, again, we need the NIC to be able to do the same functionality it did in the kernel space, but in user space. And in order to do that, we have to assign it virtual addresses to write to. It allows direct access in user space. NIC ownership is allowed also to be within a user space process, so it can do the manipulations for that, which is essentially very prohibited in a kernel space. Security for that is managed through the IOMU because it provides the isolation address translation. From an X perspective, it does see virtual addresses. It deals with them. It doesn't know that's assigned to a user space process. At the end of the day, it has a memory region they can write to without any kind of interference with the other apps running in the user space. And it also ensures that the requester NIC has rights to DMA to that region. So essentially, this is handled again by the kernel. We don't have that, so we're basically replicating that in the user space. So I'll now maybe explain on I couldn't find a better example to this, but basically on a VM in OpenStack, how the layout of the traffic looks like in a traditional layout, whenever we enable DPDK, OVS-DPDK, and whenever we enable the other solution, which is SR-IOV. So this is basically a VM, which will basically be running in a user space. It will be sending the traffic down. We'll be going here to a bridge. From that bridge, it will go down to, this is a VETH pair, which again, this is all happening in the kernel space. We have here an integration bridge, which is whether it's done using Linux bridge or OVS, or on the bottom here, we have a tunneling bridge, which is done also whether it's Linux bridge or OVS. On the right-hand side here, we have the mapping for it in the user space and the kernel space. So on top of the user space, we have the QEMU process running, which is basically the process that's sending the traffic. It's basically generating traffic inside that particular guest and sending traffic to the VirtIO driver. It goes directly to the vhostnet in the kernel space, go through the TAN-TAP device, which is a module in the kernel. From there, it engages the network stack, the bridge, Linux bridge module as well. From there, a VETH pair is engaged to map this particular VETH pair. And then we have then the OVS forwarding plane, the NIC driver, and then the NIC. Obviously, this is too much packet processing for a single packet to exit the host or to be received from a host. So OVS-DPK tries to remove all the bottom hand side, basically, by making sure that the NIC is assigned entirely to the user space. So the bottom part of the kernel space and lots of pieces in this don't happen, because we can do that inside the kernel space of the VM itself. So DPDK is a data plane development kit. It's created by Intel. It basically allows faster packet processing in user space to be done. So even with VFIO and IOMU, which is named as VTD for Intel, we can't have one NIC per application. We can't have a server with 100 NICs to host 100 VMs. So we need some sort of sharing that will happen in the user space. And we need something to do with the functionality, as I mentioned, with the kernel itself. So at a high level, DPDK provides the framework for faster packet processing. It allows custom memory management, which is, it's actually custom memory management in here, which allows you to use huge pages to allow higher TLB hits, not misses. It allows also using polling mode. So instead of having to interrupt, basically DPDK allows you to specify a process to continuously pull data out of a NIC. OVS-DPDK is an implementation of OVS, or Open vSwitch, using DPDK, and it allows switching entirely into user space. And it's based on OVS-Switch. So the diagram here, so I'll show this again, the same path. So this is very similar to sending the packet. However, it's much cheaper overhead here when you see on the right-hand side. So we see that the QEMU process will be generating a packet. It will go directly to the vhost user, which is a module or a process basically running within OVS vSwitch-D. And from there is a process in user space that directly accesses the NIC. So there is no overhead at all for the network stack. So any application that's running, whether it's QEMU or anything else, it can send packets directly from the user space to the NIC. However, it can do that using OVS in this case. Again, without the kernel network stack, we're basically left with nothing to do the translations for us for sending packets or any kind of packet manipulations, IP, TCP, and UDP. So the only way to do that will be happening in the application itself. So that traffic will basically be going from the PMDs, which is pole mode drivers here, and going directly to the DPDK NIC. So you can send much smaller packets at a very lower latency by basically ignoring the entire kernel space of the host. So this is one solution for it. The other solution that exists around there is SR-IOV, which is basically virtualization of input-output devices. It allows you to have, SR-IOV is a physical hardware feature on a NIC, which allows you to see the NIC as multiple NICs in the user space. It defines what's named as physical functions and virtual functions. You can have one physical function per NIC and many virtual functions. So you basically see virtual NICs, but the virtualization is done on the NIC itself. VMs have direct access to those VFs, and there is no host and switching overhead. So basically, we're trying to move away from the OVS. However, this comes at a price. We need something else to do the entire NIC manipulation in the user space. And to that, basically, this is targeted specifically for virtualized environments, not for application user space. In OVS-DPDK, you could easily send traffic from any application that gets attached to OVS. But for this SR-IOV, it has to be a VM, basically. VM communicates directly with the physical network using the VFs it's visible to. So what we see here, basically, two VMs in the user space, and they're connected directly to the virtual functions over the NIC. So it generates a packet, sends here directly. The isolation and all the management happens from the NIC itself and the PF driver. So to have them maybe side by side, this is how OVS-DPDK looks like, and on the right-hand side, this is how SR-IOV looks like. Both of them are just much lighter when it comes to packet processing. There is here, we see here on the right-hand side, on the bottom, there is a PF driver, which is a physical function driver. And on the left-hand side, we have the VFIO. So the VFIO will basically do pass-through for the entire NIC, and we do the partitioning for it in the user space using some sort of OVS-DPDK or some switching. And on the right-hand side, what's passed from the kernel space to the user space are the virtual functions. So you basically don't see the physical function in the user space. Both target different kind of applications. If someone is writing an application without just to run on the bare metal on the host operating system, they would normally use OVS-DPDK because they can access that switching layer that's given by that. If you're assigning that to VMs, basically it can be assigned easily using VFs on the right-hand side, whereas SR-IOV, because you have the kernel space to do all the manipulations. It will see the NIC as normal and deal with it from onboard registers, from TX and RX strings and so on. It will deal with it as if it has access to the physical NIC. So this is basically what I had for today. Thank you for your time today, and if you have any questions, I'm here to answer them. I think someone is in.
The network, but I was just wondering where's the de-encapsulation between the frame and the package happen? Is it in the NIC?
So you mean like removing the actual frames?
Yeah.
Layer 2. So this basically, I would say, happen. So I'll just go quickly to the diagram. will be happening at the link layer in here. So basically the NIC would receive the frame.
Okay.
It would know where to put it to. It would create the SK buff for it. And all the translation that happen, so that the layer 2 would get a packet that to be processed by the layer 3, if that makes any sense.
Thank you.
Next, down, I'll try and work front to back. Sorry, and then I'll jump to the back.
Thanks for a great talk. One question. Do you have any learning resources you'd recommend for people that want to know more about Linux kernel networking? Like, how did you learn this stuff so well?
Well, there's lots of talks online about it. I think there's a couple of guys who basically give very, very good talks about it. Someone from Europe, but I don't recall maybe the names or links. But obviously after the talk, I can send you all the resources I have for that.
So like YouTube?
Yeah.
You want to hand this back?
So I'm guessing the implementation of NAPI is probably sophisticated enough to handle this, but is it possible for a packet to arrive after polling is disabled, but before interrupts are enabled? Or is it somehow done in like a single atomic step?
So I think your question you're asking is about NAPI.
Yes.
And so the first packet allows you to disable interrupts. So whenever you receive a packet, the interrupts are disabled. So they will not be disabled before that. And they will be re-enabled basically when you find no packet. So you're thinking that there may be a gap in between?
Yeah.
I don't think so, but I think I'll have to get back to you on that.
Thank you.
So I think the most surprising thing that I learned is that the load balancing method is by flow, which is simply, a source and destination pair. I'm wondering, have any other solutions to the load balancing of packets been explored by the Linux kernel team?
Actually, the way I explained it is very primitive, so it's much more than that. So I maybe explained it at a very high level. It's tuples, it includes multiple things, protocol, source IPs, ports, so it's not only limited to that. I can maybe also, again, share the exact, I don't see myself like an expert in this part, so I can share maybe the links I have for that afterwards.
Is it possible to overload a system by somehow creating enough data under one flow?
Well, that's actually a very good question. I'll have to get back to you on that. No, I don't know.
Yeah, okay, pass it over here, and then I'll try. You want in the back? Full load balancing.
Another question for you. You're talking about the flows. Do you have any favorite tools, command line tools, that would let you easily observe the flows and other data structures?
Yeah, I think TC does a lot showing the basically, each tool definitely is you go to deal any kind with the NIC. TC allows you a traffic control, it allows you to see lots of things with the queuing discipline specifically. If you're playing around, I think that the best method to learn about this was to basically create a VM and do everything in it, left, right, and center.
Thanks.
I give someone in the chance in the back.
So I was wondering why have this layer of indirection between the receive and transmit ring buffers and the actual packet contents? Why not just make the receive and transmit ring buffers really, really big and stuff the whole packet in there? Like what's the advantage there?
So you're basically saying that, maybe if I understand the question properly, is that why just not write the data directly to a ring structure rather than I think this would be more efficient. But again, there's lots of things that are designed in a way that, I'm way not an expert to say that this was done because of that. There's lots of programming decisions, I think, in that. But the idea of having an address where you copy to and keeping one copy of the data, because maybe thinking about it out loud, every application or everything in the kernel space basically will have to keep accessing this ring buffer going forward. So I think a ring buffer allows you to control the amount of addresses you basically write to, and that's, as I mentioned, why packet drops happen. But in the same time, the packet buffers are limited because you can't keep writing endlessly basically to it. And I think, yeah, maybe it's even more efficient. If you don't have an RX descriptor, then you don't copy the data. So it saves you even that DMA part. If there is no address pair to write to, then you don't even do the DMA part. So if you think about it, you know, the NIC receives a packet, it gets an RX address. If it can't get one, or basically it will get one that basically overrides another one, it can stop writing for that, if it makes any sense.
Yeah, thank you.
Someone over here. Okay, back to front now.
I had two questions about the virtualized case at the end of the slides. So in both the VFIO and the SR-IOV cases, is the initial interrupt by the NIC still being serviced by the host kernel, or is that somehow getting sent directly to the kernel in the VM?
That's literally what the VFIO does. It pokes, so nothing gets serviced by the host. It gets literally entirely seen. So a DPDK-enabled NIC is not manageable at all from the kernel space. The VFIO literally pass through the entire thing. Pass-through will allow you to see directly. So from an implementation standpoint, it's basically making the entire thing visible. So whenever it interrupts the thing in the user space, not in the kernel space.
And is the IOMMU responsible for making sure that the page tables in the VM are sort of corrected? Because you've got, you know, the page tables in the host, and then the second set of page tables in the VM, so the NIC would have, you know, multiple sets to go through.
This actually happens within the, I think I know your question. So you're basically saying that does the NIC know where to write to, and is it writing directly to the VM's memory?
Because the NIC basically has to know effectively a hardware address to write
Correct.
to?
It's virtual I/O addresses, and it writes directly to the VM's memory.
You mentioned the NIC allocates the SKB. Is that the ISR that does that usually, or the softirq handler, or something else?
So the interrupt service routine would be the one that specifies how to handle, but that happens after the fact. So interrupt is raised only once the copy happens in place. So that would be basically, okay. So the packet content and the NIC itself will happen through the driver, not the interrupt.
Okay. So the driver before it even registers an interrupt.
Correct.
When it goes to NAPI polling, and it waits for the next packet in the flow, what's the order of magnitude of the wait time? There's like microseconds, nanoseconds, microseconds?
For what?
For NAPI to wait for the next packet in the flow.
Yeah, I don't have numbers, sorry on that. But,
Okay, last two, I guess.
With DPDK and SR-IOV, what impact to performance? What's the impact to performance when you're dealing with two VMs in the same bare metal host?
So maybe, okay, this actually is a diagram I'm looking for. So even if you have multiple VMs on the same host, they will all be attached in DPDK, they'll be attached to an OVS switch at the end of the day. So the trade you're doing is assigning more PMDs. Maybe something I forgot to mention is PMDs are assigned per core. So you basically use affinity to say this PMD or pull mode driver will be running on this core, and this core will be doing nothing but pulling data from the NIC. So more VMs means that you basically have to do the trade-off of assigning more PMDs because you're getting more and more packets that have to be processed.
You can have the multiple virtual switches.
But what would be the value of that? Having multiple switches on the user space?
No, your virtualization gives you ability to have multiple virtual switches. And those virtual switches are utilizing different virtual machines, and you're kind of separating them based on that, no?
I think we could do that, but the point, usually when segregation happens, OVS in the user space is not replicated, so it's segregated using VLANs. So basically, if you have multiple VMs and you don't want them to, you know, hear each other's traffic, this is layer 2 switch. So essentially, you would have multiple VLANs, and this is like the normal way OpenStack when it spins a VM, attaches it to an OVS switch. There's a separate VLAN tag for that particular project. So if you have multiple VMs from the same project, or basically the network, then they can listen to one another or communicate to one another. However, VMs from different projects will get different VLAN ID.
On your last slide, you had mentioned that with this, yeah, you can have virtual kind of NICs.
Yep.
And how much is limited? There's
So,
a limitation.
Yeah, I've seen 64. So there was Intel used to have a very predominant NIC a few years back, and when I checked, there was 64 virtual functions in it. So 64, I think, and I think 128 is not unheard of. Which basically you can assign one VF for every VM.
So
128 is it? Oh, Mellanox, yeah, of course. Yeah.
So which means you can have kind of 64 virtual machines maximum.
Correct, yeah.
On one host.
I think with nowadays, like hosts, I've seen definitely more than 128, but it will be very small VMs if you need, you know.
No, I'm talking about the small VMs.
Yeah.
So that your CPU and the memory can be utilized properly.
Correct, yeah.
So, but
that's actually true.
yeah, it depends.
All right. We should wrap just to be good.
Okay, perfect. Thank you very much for your time today. Have a good evening.